Welcome back, samurais, to the dojo. Or welcome back to the dojo, samurais. Uh, on this lesson, lesson 14, we'll be taking a step back from developing dashboards, etc. What we're going to be doing this time is we will be looking at how to fit distributions to data that we may have so that we can make some analysis on those and see what's the probability or of the 95% probability of something is represents what kind of figure, etc. And looking at how to fit our data using a package called fitdistrplus. And that's what we're going to be doing. I think probably we'll be taking around maybe 30 minutes, 35. I don't think we'll be taking the whole hour. I won't be going very deeply into the statistical and probabilistic concepts in here, but certainly that's something that you can look over at your time. So I'll be mostly uh, focusing on how we can code an analysis for using the fitdist plus package so that you can take advantage of that. Remember, for the basics and all that probabilistic theory, I recommend that you look at Wikipedia or read a book, etc. And I hope this helps you at least perform some kind of analysis at your work. With that said, let's start. So I already opened here my first script. We're not going to be using this one. We're going to be creating a new script. So I'll just be clicking over here, and then remember to create a script. Place here our script, and then there we have it. We have a new script. Now I will be making this big. Okay, and now we can probably start. Sorry, I'm setting some things up. Okay, now let's save this as, let's call it fitting dist. As always, the first thing we will do is load the library. So let's do that. Loading libraries. Let's create a section out of this, and then we will be using primarily two libraries. One of them, well, tidyverse, of course. So let's start with that one. The next one we will be using will be the fitdistrplus. Now, chances are that you don't have this installed on your system, right? So if you don't have it installed, make sure to press here, install from CRAN, packages, install, then package fitdistrplus. It'll show up here. You click that, and then you click install. Make sure that it says install dependencies, install, and then it'll run some stuff, and at the end you will have it installed. Okay. So I will not do it because I already have it installed, so I'll be pressing cancel. Okay. Now once you have that done, let's load the libraries. Okay. Let's load the tidyverse. And let's load fitdistrplus. I think I already had them loaded, so that's why we didn't see the usual information that shows up here after we load tidyverse. Right? I already had it loaded. And then that's it. Now fitdistrplus comes with a data set that we'll be using to test this out. And that data set is called ground beef. How do we access that data set? Well, we type data. Then here we will type ground beef. Now, what does the ground beef data set contain? This data set basically contains the values of serving sizes in grams collected in a French survey according to the package creators, right? For ground beef patties consumed by children under 5 years old. Right, so this is, let's write here data for serving sizes in grams for ground beef patties consumed by children under 5 years old. Okay. let's write here loading data. Then if we do this, we'll have here ground beef. We should see it in our data side. Let's click it, and then we have the serving here. Remember, these are grams. Okay, we have 254 observations. That's fine for what we want to do. That's okay. The next thing that we will do is, and just in case, because fitdistrplus, the functions that do the fitting require you to not have NAs in the data. Now ground beef does not have any NAs, right? So that means that we won't have any issues, but you may have some data that has NAs and you will need to get rid of that. So let's assume that you do have some NAs in there. So let's type here getting rid of NAs. NAs in dataset. Data frame. And for this we'll do ground beef. And then ground beef again. Pipe operator. Oops, sure, not this one. Like this. Ground beef na.omit, and that's it. We should still keep the same thing. If you see, it's 254 because it had no NAs. But with this, you should be getting rid of that. Now remember, ground beef only has one column, right? If you had more columns in here that had NAs, maybe you would end up eliminating some other rows. So make sure that you're careful to select just the column that you want to focus on your data frame, and maybe just after selecting that column that you're interested in, then eliminating the NAs, because of what I told you. It could end up, I think NA omit goes or looks at the whole data frame and then it'll just drop things. I think, okay, don't quote me on that one. Great, now we have our data. Next thing we'll do is we'll show some general information about the data set. So let's type here showing general information about dataset. That might be statistically relevant or probabilistically relevant, let's say, just to get an idea of how this is looking. So we will be using a function. The first function that we'll use from the fitdistrplus package will be something called plotdist. And plotdist will give us an idea of what the dataset is like. Histogram, we want a histogram, and we also want and let's see, it's plotdist, sorry, yeah, see, and then we also want the cumulative distribution, right? So now we have here a graph that looks at how the data looks in a histogram. What's the cumulative distribution looking kind of like, and it gives us an idea. Okay, what else can we see from here, right? So pretty nice graph. You know, if you want to include this in an R Markdown document, then you can of course do this. Of course, if you want something much more, let's say, unique, you would have to code the plots for this. But if you're not in a rush to do a lot of customization, then I just recommend that you use this function by itself. Okay, so we'll be closing this. Now that we have a general idea of how our data looks and how the cumulative distribution function looks like, well, at least according to our data, right? These are real data points. This is nothing, it's not fitting anything. Then we will look at some, let's say, we'll look at the data that we have, then we'll bootstrap some values to see where our data could end up like, plus where our actual data ends up. And then we'll have several, let's say, we'll have a graph. The good thing about fitdistrplus is that there's a function that shows several distributions and where your data kind of lands in. plus the bootstrap values, and then you can take a decision like, okay, I think this function might be good to this distribution might be good to use, or this other one might be good to use. So how do we do that? We will be using a function called this dist. So it's like this. He says here, description of an empirical distribution for non-censored data, computes the descriptive parameters of an empirical distribution for non-censored data, and provides a skewness kurtosis plot. Yeah, that sounds very complicated, but I think what you need to remember is probably what lands closer to your data. So let's go around, and then say providing descriptive statistics. Let's call it. So desk dist, this ground beef, serving, and then like I said, where you say boot, for example, yeah, values of skewness and kurtosis are plotted from bootstrap samples of data. So boot will be, let's say, just 1,000. And there we have some summary statistics, as you can see. We have min, the max, the median, the mean, the standard distribution. No, standard deviation, sorry. Standard deviation, and then skewness and kurtosis. Now you can also save this in case you want to, let's say this is the result, but you can also save this into something. So let's call it desk, just for the sake of it. And there you have it, and this has a list of, if you open this, it has a list, so you can actually access information from here. For example, let's say that you type desk min, it's 10. You will look at this, it's 10. So you can also save that information and then later pull it out for a report or something in R Markdown. This is not an R Markdown document, this is JavaScript, but of course with the knowledge that you have on R Markdown, you could also be creating an R Markdown document that is publishing this information and including it in sentences, for example. Okay, now we go into the important part. Now that we have a general idea of how our data looks, right, we have here several distributions, the theoretical ones: normal, uniform, exponential, logistic, beta, log normal, gamma. Each of these distributions has a lot of theory behind them, so if you're interested, please read into that. Then we have here all actual data, where it lands, and then our bootstrap data, which is just like made up data, you know, where would it land. So we can see that we could use maybe a beta, or maybe a gamma would be the closest ones to our data point. Okay, I'm not gonna be focusing too much on which one we use. I'll show you how you can test several ones, and then in the end, with more knowledge, you can select which one you want to use. So let me close this. And next we'll be doing here fitting distributions. And to fit distributions, let's call this, we're going to be fitting several ones. We're going to be fitting, let's focus on 4: y-bool, gamma, log normal, and normal. Like I said, you don't need to, I will not be discussing the meaning behind all these different distributions, but I'll show you how you can fit several at once, and then you can read more on that yourself. Otherwise, you know, we can take classes and classes just talking about this. Fitdist is the function that we will be using for this. Oh, by the way, before we go into this one, I just wanted to talk about something that I don't use a lot of the time, but let's say that you wanted to use a select, and then that we wanted to select here serving. this probably will not work. So sometimes when you load tidyverse and fitdistrplus, I think fitdistrplus masks a function called select, right? So if I think if we type select, yeah, see, you have two selects here, and I think what happens and ends up happening is I think that the fitdistrplus is ends up masking one of those for some reason. If that happens, you can always remember you can always call a function from a particular package by typing dippler, because we know the select is a dippler function, colon, and then it should work. I actually here need to remove this, and there we go. See, we no longer have that mistake. Okay, with that parenthesis ended, because I really want you to show this, because I think maybe I mentioned it before, maybe I didn't, but sometimes when something is masked, you need to definitely type the name of the package, colon, and then the function in that package. If we don't type this, like I said, it's masked by another function, and then it'll keep giving you problems. So just in case you ever run into that issue when using tidyverse and fitdistrplus, then you know how to fix it. Okay, going back to fitting the distribution, we'll do fitdist, which is the function to fit distributions. Then we'll be calling our data ground beef. We will be looking into serving, right? Here we're accessing serving, right? Ground beef, money sign, access, serving data. And then we will write here the distribution we want to fit, and then method equal maximum likelihood estimation, MLE. There are other methods to fit data. I'll be just looking at MLE. If you type here fitdist, you should be looking at different methods: MLE, MME, QME, etc., MSE, MGE. You can read more on those somewhere else, right? If you don't want to too much, just keep MLE, I would say. But each one of these may require different attributes that you need to provide. I can't remember exactly. But yeah, we'll be using maximum likelihood estimation in this particular exercise. And then we're going to be looking at a summary of FW, just so that you know that you can look at the summary of what this fitting looks like. Okay, so we have our desk, this, and before we run this, basically what I will do is copy this again and fit other distributions in here. So Weibull, I'll try gamma, so let's call this one FG, F for gamma. Then let's also try, let's say, log normal, and let's call this FLN, and finally let's go for one last one. That last one will be the normal distribution. Norm, and this one we'll call F norm. Okay, now we have our fitting of distributions done, at least coded. Let's execute this. L norm, actually this is L norm, not L normal. There we go. F norm, okay. So let's see, done. Okay, we have all of them now, and you can see a summary, like I said, using the summary function and then passing a fitdist object, which is FW. For example, I saved things in FW. It has a list of several attributes, And by using the summary function, you can look at the estimate, standard error, the and some other log likelihood estimations, AIC and BIC. What did what? Let's see. No, it's okay. Yeah, I won't be going over this, but if you can look it up, AIC and BIC. Actually, let's do it. I think AIC. Well, I think it's probably easier to just type AIC statistics, and then yeah, here you have it. AIC and BIC. You have the archaic information criterion, all the information related to it, the definition, blah blah blah, and the Bayesian information criterion also. So you have all that in that summary, and these numbers are good and can be used to, compare things and see what actually fits better. But I will not be going into any of those topics. I'll just be focusing on how you can fit distributions, look at summaries, and then maybe do some analysis with whatever distribution is it that you end up choosing. Okay, now that we have everything done here and fitted, we will be using a function called par, and this one is we can use this function to create a graph that will contain more graphs in it, right? So I'll be showing how that looks like. So it's like par, and then mf row equal, passing a vector 2,2. Then we will look into mar equal, which is mar for margins, I believe. So now the vector 4, 4, 2, 1. So these are the margins for the plots, and if you modify this, you're basically modifying how much space the graphs occupy. 2, 2, basically how many, it's a grid of 2 times 2, so we will have basically 4 graphs in there. Okay, then we will go into plot.legend. We'll be saving this as a vector. So this is what our legend will say in our graph. And normal. Okay. And then we will proceed to create the different plots that will be contained in our graph. Okay. And we will get several graphs. We'll get a QQ plot, a PP plot, a cumulative distribution function, and I think also a histogram. So let's see how that gets done. So we'll use the function densecomp, and then we'll be passing a list, and that list will contain the different distributions with it: FW, FG, FLN, FNorm. So FW, FG, FLN, FNorm, comma, legend text equal legend, plot dot legend, which is the vector we created. So we're gonna pass that legend into this function so that it labels things correctly. Okay, then we will do a QQ plot, and just bear with me, I'm typing everything. We'll see how everything looks in the end, and then we do exactly the same thing. Actually, I'm just gonna copy this. Then we will do a CDF Go to distribution, same thing again, pass the same parameters. Why is this? Okay, here, that's why. Okay, and then app plot. Okay, there we have it. Now let's save this and let's just run this the second part of the. Actually, let's delete everything. Let's clear everything here. Let's start from scratch. We didn't need to learn to load the libraries again, but I did it just in case. So we have our first graph, second graph, fitting our distributions, creating the legend, and there we go. See, every time I press, a new plot gets added. And what is it that we're watching here? I think maybe this is something that should probably be explained a little bit, otherwise it doesn't really matter what we're having here. We'll start with this one. I don't think I need to explain. This is just a histogram, right? And how the different distributions look compared to that histogram of data that you have. In this case, it's the ground beef serving sizes for children under 5, according to a French survey. And we have our different distributions that we tested. Weibull, gamma, log normal, normal, which are the ones that we passed on. Then, by the way, it's important that you keep things in order, right? If Weibull is FW, gamma is FG, log normal is FLN, and normal is FNorm, right? And if you mislabel this, you could have issues. So be very, very careful with how you label your legend and how you're passing down the arguments in your list. Don't switch the order, so you could have problems. Okay, with that said, this is pretty self-explanatory. This graph over here. Next, let's look at our QQ plot. What is a QQ plot? A QQ plot stands for quantile plot, and it basically compares quantiles of the data to the theoretical distribution, and it's good for checking the distribution shape, particularly in the tails of the distribution, right? So this part over here and this part over here. So we have a line here that is at 45 degrees. So the closer that these dots fall into this line, the better that particular distribution is at looking at the tail data, right? The closer the better it is. The further away it is, that means it's worse. Then not only do we have that, we have what's above the line and what's below the line. If the data is above it, that represents a more extreme value, right? And it's also known as a heavy tail, I believe. And this is if you fall above this 45 degree line. If you fall below it, that would be a light tail. And yeah, basically fewer extreme values, let's say. So it's important, I think, to remember that the closer you are to the line, the better. If you fall above, that means higher likelihood of extreme values in the tails. If you fall below, less likelihood of extreme values. That's what you should remember about the QQ plot. After that, we have empirical and theoretical cumulative distributions, right? We have here the empirical ones, which is the real data, and then we have the theoretical cumulative distribution functions for Weibull, gamma, log normal, and normal that we fitted. And you can see how well those different distributions fit to the data that we have. Of course, there's no perfect fit, right? There's never a perfect fit. So you can just look at, okay, which one, just by observing, because you can also do this just by observing, not looking at the data itself. And you can choose basically which one you want to, well, all these different graphs allow you to probably pick one that is probably better for your particular need. It's rare that one cumulative distribution function would work for everything that you want. Maybe you might want something that is less extreme values or a much better fit in the tails, then the QQ plot would you be looking at. If you want something that is more reliable with the mid of the with the average values, with the middle part, not the tails of your data, then you might be looking at a distribution that has a better PP uh, graph, right? The PP plot basically it compares the cumulative probabilities of the data to the theoretical distribution. Of course, again, there's a 45-degree line here, and it's a good check for the overall fitness of goodness of fit of that distribution. Points above the diagonal line, these ones suggest that the sample data accumulates probability faster than the theoretical distribution, right? And points below the diagonal indicates that the sample data accumulates probability more slowly than the theoretical distribution. Okay, so that's what's important to remember about the PP plot. And remember, the closer you are to the middle with your different distributions, the better. If you're further away, well, you know what that means. If you're above or below, you accumulate probability faster or slower. And I think that's it. I think we've gone through all the four graphs. Right, so this is very nice to include in your analysis. You can have more distributions here. We just stuck to 4, right? And then from here you can choose like, okay, which one do I want to use? Okay, so I'll be closing this one. Now that we have our distributions, right? Let's look at, let's try to get some predictions out of it. So let's say predicting, let's call it predicting. And let's look at that prediction using all the different distributions so that we see how they affect, right? How they're different. Predicting what 90% of beef servings are like in each distribution. That we fit. Okay, so for that, I'll be saving this into something called serving. Now I'll reuse the same variable, but you can of course do something different here and label this serving W, serving gamma, serving Y will, serving gamma, serving log normal, serving F, serving normal. I'm just going to be using serving just because, right? Actually, screw it. Let's do it properly. Let's say serving W for serving Y will. And we'll be using a function called quantile. We will pass the FW, which is the distribution for Y will object. Then the probs, or the probability of 0.9, which is what we want to obtain. And then serving W, I want to show that quantile 1. So let's see, serving W we have, then the quantile. So we know that 90% of the times we have a value that is less than or equal to 122.06 grams, according to the Weibull distribution. And we can do the same prediction for the rest of the distributions. So this is, let's call it Weibull for servings. Actually, it's Weibull double L. here we'll add next, which was the next one? Gamma. Oh, here FG. There we go. Then we will copy this again. We'll paste it 2 more times. Serving norm FLN, which is for the normal. Then this one, let's call it F norm. Norm, L norm, and let's see. G. There we go. Now we have the different predictions of at 90, right? What the value would be according to each of our distributions. Like I said, you can choose which one fits your needs better, right? By looking at the graphs. And then you can proceed with your analysis, or once you're happy with that. If you want to know the parameters of all these different things, you can actually look at the parameters that they have. And here, for example, I'm accessing certain information, but there's also different ways in which you can access this. So let's see how that looks like. If I press here, let's say serving W, money sign, quantiles, you see this is with the result that we have. Yeah, actually it's better to access it like I did here. But there's another way in which you can access things, and I will be showing you that slightly short in a short time. So we already have what we, the different according to our fitted distribution, what value we could get according to whatever percent that you can think of, right? So you can already use it to make predictions. But what if you want to go the other way around and say like, hey, I want to know what the value of, let's go for the normal, of 119.5434 grams represents in probability. We know that it represents 90%, so let's recreate that. Okay, so for that you would use a function that will vary according to the distribution. In this case we're using the normal distributions, so you would use p norm. But like I said, I think there's a p Weibull too, right? So according to distribution, you need to type P and then the name of the distribution. You'll probably have to check the documentation to see if you're typing the right function. In this case, I know that it's P norm. So P norm, and then for P norm, I want to provide I need to provide the value, which is 119.5434, and then I need to provide some information related to the mean and also to the standard deviation, which is a parameter that P norm will require. And this will vary, of course, depending on the distribution you're using. In the case of P norm, we need to provide two things: the mean and the standard deviation. Here we will type F and SD, right? And we can access things in F norm. You see, we have many things. We have SD here. We have somewhere we should have the let's see here in estimate, sorry. Oh, but this is FW, sorry. It's F norm. Here we have mean and standard deviation in the estimate. So one way of accessing that is by typing F norm, money sign, estimate, and then we can write brackets and type mean, which is the mean here, estimate, mean, and then we can do exactly the same thing and type F norm, money sign, estimate, SD, which should be this over here. Okay. Finally, let's save this. By the way, I don't think we have saved. And let's see, if we execute this, we see that 119.5434 represents the 90th percent. If we type here, let's say 110, we'll see that's 84, right? So 84%. So that means that 84% of the times you have a value that is less or equal to 110. Okay. And then I think, I believe that should conclude our tutorial for today. Yeah, it's very, very simple to create an analysis, a statistical analysis, and make predictions, etc. With fitdistrplus, how to fit those distributions, how to visualize the data, how to interpret the QQ plot, the PP plot, the theoretical densities, and then, you know, once you have all that information, to make predictions. Like I said, this code will give you all those values, but I think there's much more value in writing this instead of a script, instead of writing as a script, to write it as an R Markdown document. That way you can already dynamically pull that information and write a narrative using different distributions or whatever is it that you want to do. So that's also good knowledge to remember. Now, with that said, I believe we have come to the end of our training today. Yeah, I don't think we'll be revisiting this topic again on how to use fitdistrplus, etc. Like every single time, there's a lot more to learn about each package, right? I'm just giving you a little bit of things that you might find really, really useful for your work, right? And this is one of those things. If you're more interested in learning a lot about the package, please read the documentation. Please look at their website. You'll be able to find much more information. Okay, now with that said, and actually this particular example is for ground beef, and how this analysis was done is very similar to how the author does it. Basically borrowed it from them. So credit to that goes to them. I just added a few tweaks here and there. With that said, thank you very much for attending today's lesson. I hope that you enjoyed it. I hope that you continue to add tools to your arsenal of data analytics, data analysis in R. Next time, we'll see if we go back to Shiny or if we take another detour to continue building our competency. And eventually, we'll definitely end up again looking into Shiny app development. We roughly did something that is kind of similar a little bit with Flex Dashboard, but we will be looking more into much more detail over there. Yeah, that's it. With that, thank you very much for joining today's class. I hope that it was useful for you. If you like what I do, please like and subscribe or comment. Help me feed the YouTube algorithm so that these lessons end up showing for more people. I would significantly appreciate it. Help me help more people. Basically, that's what I want to do, and it would mean the world to me if you can help me do that. With that said, make sure to save your work, and I'll see you next time. Class dismissed. Have a great day.